So here we are on the back side of the worksheet that I gave you yesterday, and we're looking to identify the types of reactions we're going to see today. Some are going to be new from yesterday, and we're going to try to write the products and the reactants correctly, formulas, and we're going to try to balance. And we should know why we balance. We try to balance to make good cake, which I always say, which means we're trying to balance so that we know how much of each element we need in order to maximize a chemical reaction so there's no waste. So we had this reaction yesterday. We saw this up close and personal with a demonstration. We had two hydrogens and one oxygen to make two water molecules. This is a 2 to 1 to 2 ratio. And this is exactly how much I need. I need a 2 to 1. If you saw those balloons blowing up, where we had a 2 to 1 ratio is where we had the most energy released, the best reaction. So in any case, let's get started. So we have number 4. Number 4 of iron 3 carbonate. I see that's the only thing that is present in my reactant. The question is, what's happening here? Well, it must mean that iron carbonate is going to break apart into pieces because it's together. And how do I know that? Well, if you look very carefully in the reaction we did yesterday, we've got water that was built from its pieces. What do we call this? We call this a synthesis reaction. In a synthesis reaction, we're making something from its elements normally, or from pieces. Here, it looks like we're going to the opposite, and we are. What we have is, let's pretend we have A hooked up with B. Now that could be iron is A and carbonate B, and it's breaking apart into A and B. That's breaking apart or decaying or decomposing. You got it, it's called decomposition. So please write that. Yeah. Decomposition. So how do we do this? Well, we first must be able to write correct chemical formulas in all of this, because if you can't do that, this skill in balancing and writing formula writing is going to be difficult, if not impossible. So iron 3, people get this wrong all the time. What does that mean? I'm waiting for an answer. Someone speak. Thank you. Now iron, that's right, means iron plus 3. Now why do they do that? Iron has two possibilities. Look right here. It can be +2 or +3. It's a transitional metal that has multiple, we call these oxidation states. So if we're dealing with iron or any element that's got multiple oxidation states, when you write the name, you have to tell me what ion we are using. So this is saying that iron is using the +3 if it's iron 3. So you really have to identify that Roman numeral 3 means exactly the charge that ion is. That's what it is. It's not the third choice. There isn't. It's not that we need 3 irons. It's that iron is +3 in this case. Now, carbonate. What the heck is a carbonate? If it was carbide, it'd just be carbon. If something ends in IDE, it's binary. But carbonate is one of those clusters of ions we call polyatomic ions, and there's a place to look, and I call it the what the heck is that table. Let's go to table E. And here is our list of selected polyatomic ions. Certainly not all of them, but enough that we can use. And here it is. So we are looking for a carbonate, and I have found it. Carbonate, I'm in the what the heck is that table. It's a cluster of non-metals normally. Okay, there are some metals here, but there's my cluster. It's a carbonate. It's CO3 -2. Okay, so CO3 -2. So this whole cluster is -2. This is +3. So what we do is you can crisscross. They're salts, so they have to be in their lowest form. So I'll need 2 for the iron and 3 for the carbonate. Now, if you're going to do this work and show the ions to build, once you build the formula, you have to get rid of these ions. So what we're going to do is, this is a -2, so you need 2 of these. Let's try this. 2 of these, and because it's +3, we need 3 of these. Nobody wants to see your ions anywhere. Put your ions away, please. Don't leave them out. Okay, you use them to build a formula, then you get rid of them. It's impolite to keep your ions out. Okay, so now we've got the correct chemical formula. Now we have to find the pieces. What is iron made up of? Well, iron's made up of iron 3 carbonate. What is it made up of? Well, it's made up of an iron. Those are the pieces. It's made up of a carbon. I'm just going to split this into its elements and oxygen. Okay. Now, let's see if we can balance a little bit. We have 2 irons, so I throw a 2 here. And when you balance, party people, you have to make sure that you're just putting coefficients in front. So 2 irons. This 3 means I have 3 carbonates, so that means how many carbons do I have? That's right, good job in the second row. That is 3 carbons. And 3 times 3 is what? Oh, 9 oxygens. Anything bothering anybody right now in terms of chemistry? Personal issues I cannot take. Okay, the problem we have right now is that, well, you've got this oxygen sitting here. And we should know something. It's a mnemonic called the Hofbrinkels, right? Anytime you've got an element that's part of the Hofbrinkels or the Brinkelhof, depending on how you learn it, these guys, of course, are all diatomic. So this has to be O2. Now look at what I'm balancing here. I have 2 irons, 3 carbons, and I have to have an O2 here. So that kind of changes my balancing, so let's get rid of that. All right, so we're back at the drawing board here. And so we have 2 irons. We'll put a 2 here. Let's put that in a different color because I can. I have 3 carbons. All right, that's fine. Now I need 9 oxygens. Whoa, how can I have 9 oxygens when I can only have an even number, right? Put a 2 in front, that's 4. Put a 3 in front, that's 3 times 2 is 6. I can have 8 or 10, but I can't have 9. So what I'm going to do is, I know 9 plus 9 is 18, so 2 9s will give me an even number. So I'm going to throw a 2 in front. And you notice something, there is never one way to balance everything. Like I've talked about before, it's a puzzle. And you could go about a puzzle any way. Nobody teaches someone how to do a crossword puzzle by doing it only one way. There's so many ways to complete this. So I'm kind of just working out my thoughts, but you certainly can come to the end product different ways. But I'm going to double this because to get 9 oxygens, it's impossible because I got a 2 here. But if I go 9 plus 9, 18 is an even number. So watch what I do here. So 2 here, this gives me how many irons? Oh yeah, that's 4. And sometimes you're going to have to erase and scratch out to figure these out. That's 4. Then you have 3 carbons. We had 3 carbons if there's what? 1 of these. But the 2 in front distributes. 2 times 2 is 4 irons. Now there's normally 3 carbons per what? Per 1 of these, right? But 2 times 3 makes it have 6. So there's 6 carbons. So this becomes 6. And 3 times 3 is 9, but times 2, right? There's 2 of these. Normally in 1 of these there's 9, right? In 1 of these there's 9. 2 times 9 is 18. And how do I get 18 over here with a 2? I put a 9 here. Now if you're getting lost a little bit here with this 3 and the 2 thing, here's what I normally do. I get a map. Now, draw the ions out. 3 of these carbonate ions means you have what? You have a CO3 that's -2, and you have 3 of them. CO3, -2, CO3, oops, that's a doohickey, it happens. CO3, -2. I have 3 of them. These are clusters. I like to circle them to show that these stick together. All right, they're like my A's and B's over here. Now, how many carbons do I have? Of course I've got 3. How many oxygens? 3 plus 3 is 9. So 3 carbons, and of course I've got 9 oxygens. Now if you put a 2 in front, well, okay, let's forget. We have what? 2 irons. 2 iron plus 3s. Can't forget that. Okay. And they're ions as well. So nothing's really bonded. Don't fall in love with the fact that Fe is really this bonded to itself. It's not. It's 2 of these ions. So you have 1, 2, 3, 4, 5 ions here. Now per 1 of these you have 2 irons and 3 carbons and 9 oxygens. But what if I was to double everything right here? What if I was to double all of this? Wouldn't that be now 6 carbons? Don't know why I drew an X. 6 carbons and 18 oxygens? Yeah, so sometimes thinking about what these really are outside of the parentheses can help. All right, so that was a doozy a little bit, but definitely doable. And you should try it again on your own at some point. All right, so that's what we have here. So the balanced chemical formula is a 2 to 4 to 6 to 9 ratio. And we're looking usually for the lowest whole numbers. And we do have that there. Okay? All right, let's move forward. Number 5. Number 5 is not decomposition because it's not together. It is not one big thing coming together. So what am I going to make here? Well, I'll walk you through this one. This is a new type. What we have is zinc, and zinc's a metal. We have hydrochloric acid. What I'm going to do is I'm going to start drawing an orange line through my positives and negatives. So I'm going to draw a line right through this. Helps me think that the first, okay, ion is always going to be positive. The second ion is going to be negative. Now I know H is +1 here. All right, now I know it for a couple of reasons. When they put the element in front is almost always plus. That means the element in the back has to be negative. Why do I know that? Because if there's one H that's positive, this has to be one chlorine that's negative. If I'm not sure, please, I really ask you to look at your periodic table. Look at hydrogen. It can be +1 or -1, but because it's in front, it's +1, just like, okay, now chlorine is -1, +1, +3, +5. So which one do I pick? Well, if H is +1, every chemical formula has to be electrically neutral, so this has to be -1. It's only got one negative choice. Zinc, as we learned, has no charge because it's an atom. Protons equal electrons. So what's going to happen here? What kind of reaction is this? What's going on? Well, let's figure it out. Okay, first, if I show you how it works, maybe you understand. This is the reaction that I made hydrogen gas from. Now, certainly I don't want you memorizing, but watch what happens. Zinc has 2 valence electrons pretty much, and it's a transition, well, we'll just say it has 2 valence electrons. Okay, it has electrons to give because it is a metal. Metals hold on to electrons loosely. Now, H pluses are very attracted to electrons. So what this does is, this is able to pull the electrons away from the zinc. And when you pull electrons away from the zinc, when an H plus gains an electron, you make, guess what? A hydrogen atom. It's H plus, meaning it's missing an electron. And now when it gains an electron by the metal giving it up because they're bigger, they hold on to electrons loosely, okay, they become an element. However, don't forget, it's a what? Hydrogen is one of those what? Brinkelhofs or Hofbrinkels. So it's an H2. Nice. Okay, what else do we have? Well, once zinc loses its valence electrons, it becomes what? Zinc +2. Now, if you didn't know that, where do we go? We go to that periodic table. There it is. Zinc becomes +2 when it bonds with something. So when it wasn't bonded, it was 0. It was an atom or an element. But when it bonds to something, it's +2. The two, basically, each hydrogen or 2 hydrogens grabbed each electron for zinc to be +2. Chlorine is still -1, so chlorine sits right there. And it's -1. And this is the point where people tend to make mistakes. Okay, they think that, well, if the zinc is going to replace the H, right, because the H is going to pull electrons, so what really happens here, by the transfer of electrons between the nonmetal, from the metal to the nonmetal, right, nonmetals are what? Like hydrogen, going to grab electrons. What the zinc does, it basically kicks out the H, and the H is free. So it single replaces with the chlorine. But the biggest mistake is people say, okay, the zinc comes in and I put it next to this Cl and I'm done. No, you have to write correct chemical formulas right there, right there. So we have to put this together so that this compound now is electrically neutral. Well, if zinc is +2 and chlorine's -1, it's not going to be a 1-to-1. Now, if you like, you can crisscross and make sure you're in lowest ratio. Okay, so -1 was going to go here, the +2 goes here, and it's always going to be the absolute value of those crisscrossing if you do it that way. So you need 1 zinc for 2 chlorines. I like to think that, hey, if chlorine's -1 and zinc is +2, I need 2 of these ions. So got to put your ions away. That's right, don't leave them out. Once you build your formula, put your ions away. So what we have is zinc is +2 and chlorine's -1. So if you do crisscross, this is a +2 here, it's going to be 2 and a 1, and this is zinc chloride. This makes it an electrically neutral compound. So now we're ready to roll. We're ready to balance. Let's do so. 1 zinc, 1 zinc. I have 1 H. I have 2 H's. No good. So to get 2 H's, what I do is I put a 2 in front. All I can do when I balance is put coefficients in front. I can't start changing this. Can't put a 2 as a subscript. That's based on, as we talked about in the first side of the sheet, based on your what? Lewis dot diagrams. Things bond only in a certain way. 2 H's, 2 H's, 2 chlorines, 2 chlorines were balanced. Same number of atoms and same types on both sides. But we're still left with the $2 question, not a $1 million question. What kind of reaction is this? Well, this is called a single replacement reaction. Why is it single replacement? Because only one atom, or I should say one element, is replacing a compound. So you're pushing out one element for another, or one ion for another. Okay, for example, if I have A by itself, which is my zinc, plus a compound that's bonded to like hydrochloric acid, so that's like, let's say B is your H plus, and Cl is your C here, what happens? Well, the A is going to kick out a B, and the B goes by itself, and you're left with a single replaced product, which would be, in this case, AC, and B is free. Now, don't fall in love with that, the idea that zinc comes with the chlorine, that's it. No, you have to write what? Correct chemical formulas in these positions. The new chemical formulas. You've got to write new chemical formulas here and make sure they're correct. Okay, so let's continue on. Number 6. Let's look at this reaction. What kind of reaction do you think number 6 is, just by looking at the reactants? You guessed it. Okay, now if you didn't guess it, look what I'm going to do. I'm going to basically split down, okay, the orange from my positives to negatives. So I'm going to put a line down the middle. It was supposed to be orange. Okay, I am colorblind. So let's put this right down the middle. My positives are over here. My negatives are on the, positives are in front and my negatives are behind. So potassium's a group 1 metal. It's +1. And if you don't know that by now, you go to the periodic table. Okay? And sulfur, if you look on the periodic table, is -2. It's a nonmetal. Calcium is +2. Bromide is -1. What's going to happen here? What's going to happen here? Well, it's not going to single replace because you have 2 things here. Could it be that this positive could somehow hook up with this negative? That would be a replacement. And couldn't this positive hook up with this negative? And that would be a replacement. In fact, we would have 2 things replacing. What's the name? We call this a double replacement reaction. Okay, in the single replacement, one thing kicked out the other. Okay, let's draw a model of this to make some sense. So in this case, I have an A ion attracting a B ion, okay? And very simplistic case. And I have a C ion attracting a D ion. These are my reactants, just like I have here. I split them in half. The positive side, the negative side. The positive side, the negative side. Now, what's going to happen is the positive front is going to hook up with the negative. Hey. And what's it going to make? It's going to make A hooked up with D. Okay, and what else is going to happen? We're going to have the positive C hook up with the B, right? Because when you break them right down the middle, the one in front is positive and the one behind trailing is negative. So you're just going to switch partners. The positive hooks up with the negative, positive, and they double replace. And of course, what you're going to make is C replaces the B with A, and you make C. And notice I put C in front because the positive one goes in front in our naming system. And this is called a double replacement. This could not be up here, number 5, be a double replacement because it only had one element double. So let's get back to our work here. So I've got potassium is going to hook up, the positive potassium hooks up with the negative bromide. Don't do this. Hey, K replaces the Br, I'm cool, I'm ready to rock and roll. Wrong. Br isn't really Br stuck together. It means what? 2 Br negatives. We have to rebuild, okay, in this position. We have to rebuild brand new compounds. We start with our ions, right? K is plus 1. One of these bromide ions is what? -1. Hey, that's a 1-to-1 relationship, so when we crisscross, we get K Br. Not KrBr2. Br2 doesn't exist. It's 2 bromide ions. What else do I have? So I took the K with the Br. Now I'm going to take the calcium with the sulfur. Calcium is, it's a doohickey, sorry. Calcium is +2. And the sulfur is -2. And all I'm getting these are from the periodic table. I don't have to show you anymore. Hey, that's also a 1-to-1. Notice, okay, notice I'm tall. No, you can't notice them, it's a video. But notice it's a 1-to-1, not much to notice. So I'm going to get rid of my ions, right? Get rid of your ions, put them away. Once you're ready to build a chemical formula, I don't want to see them, so it becomes CAS. +2 and a -2, you crisscross, reduce to lowest terms. Now let's balance. Okay, there are 2 potassiums here, 1 potassium. The only thing I can do is put a coefficient in front. I can't just throw a 2 there. That doesn't work. If Br is -1 and K is +1, you just can't arbitrarily change and break science right there. You have to stick by how these actually exist. So you can only put these ratios in front called coefficients. So 2 Ks. Whoa, this gives me 2 Brs because of the distributive property. Oh, I already have 2 Brs. Cool. All right, and I have 1 calcium, 1 sulfur, 1 sulfur. If you want, you can put the 1s in front, doesn't matter. And this is balanced now. And we wrote the correct chemical formulas, and we identified the reaction. A lot going on. So we have basically 4 different reactions you are responsible learning right now. We have something called, as we did yesterday, when you make something from its elements, it's a synthesis reaction. The reverse of a synthesis, where you have this thing breaking apart into its pieces, is called decomposition, decomposing. Then if we have 2 reactants, and one can single replace because you have a scenario with an A and a BC, and one kicks out the other, you have a single replacement. If you've got 2 ions in each reactant, you're going to have a double replacement. Okay, so let's stop the video and let's try to see if we can do we're going to do number 7 together. So let's do that, okay, because I want to make a point here. So if we look at this one, right now, can someone tell me what kind of reaction do I have by looking at number 7? All right, sounds like no one wants to answer. So I'm going to split my positive and negatives together. Watch what I do here. I'm going to split the aluminum from the nitrate. Why? Because I know the positive one's in front, and specifically I know aluminum is +3 from the periodic table. What the heck is this cluster? It's a what? It's a nitrate ion. And what's its charge? Well, from table E, the charge is, so the charge is, of course, -1 for this total cluster. I got it this time. So this whole thing is -1 individually. Okay, I'm going to split this one down the middle. This sulfate, what the heck is that cluster? Where do I go? I go to table E. What the heck? Sulfates are -2 per each cluster in table E. So if the sulfate is -2, it makes my copper +2. Now, why didn't I look up copper immediately? Because there's something that I know from experience that copper has that aluminum doesn't. Let's go see in the periodic table. Copper has multiple oxidation states, so I had to figure out which one I had, and I did so by looking at the other ion. So sulfate was -2 and there was only one of them, so I knew that copper was +2 because there was only one of them, a 1-to-1 relationship. All right, let's double replace now. Oops, I kind of gave it away, right? Couldn't the positive hook up with this negative? Yes, yes, sirree. Okay, so aluminum, which we know is +3, and sulfate sticks together. It's a cluster, it's SO4 -2. Okay, so how do we write this chemical formula? We have to rewrite a new one. Well, we put the 2 here, crisscross, and go to lowest terms, 3. All right, so I need 2 aluminums for 3 sulfate ions. So I'm going to put my ions away. All right, get rid of them, don't be rude. And I write my sulfate. And I needed 2 of those, and I needed 3 of these. Okay, now who else am I going to double replace with? Because if this positive goes with this negative, couldn't this positive hook up with this negative? Yeah, but what's the positive? So you had to know what copper was. So if you thought copper was +1, you might go, okay, 1 copper. Hey, each nitrate's -1. Notice I'm right, and you'd say, oh, I'm done. But because copper is +2, and we figured it out by looking at the other ion, this can't happen. Because if this is -1 and this is +2, how can I make this equal 0? Well, the 2 comes down for the nitrate, the -1 is here. So clearly, hope you can see that we would need 2 nitrates, right? Crisscrossing, the +2 comes down here, and the -1, or just one of them, it's always the positive value, is 1 here. Put your ions away. Oops. Put your ions away. Okay. And let's write the chemical formula, which is going to be, of course, 2 of these. And now, let's balance. Now I'm going to get rid of this stuff here so we can make this nice and clear so we can see what's going on. This is an important point. We're dealing with polyatomic ions here, and it can muddy the waters a little bit because you can get lost in the shuffle of what's going on. Now, we have one, let's balance this. 1 aluminum, 2 aluminums. I'm going to throw a 2 here. That's not the period, that's my period well here. Okay, so 2 aluminums, 2 aluminums. Now you could look at the nitrogens and the oxygens individually, and you're going to make yourself go nuts because they're all over the place. I suggest, and this is very important, pick your head ups, please. This is the most important part. If you have polyatomic ions that stick together, I suggest that you keep them together. So, if in one of these, how many clusters of nitrates do I have? I have 3. So, if I have a 2 in front, doesn't that make me have 6 nitrate ions? See, I'm keeping this together right here. I'm treating that as an element. So I have 3 of those. Normally when I have 1 of these, but I have 2 in front. 2 times 3 is, yeah, that's right. I have 6 nitrates. Well, on this side, how many nitrates do I have? I've got 2. So to get 6 nitrates, I put a 3 in front. This gives me 3 coppers. Over here I have 1, so I put a 3. This gives me, by the distributive property, right, 3 coppers, 3 sulfates. Keep your what? Keep your sulfates together if you can. There's a sulfate. So I have 3 sulfates, and lo and behold, if you look carefully, I've got 3 sulfates. 2 aluminum, 2 aluminum. I have the same number of stuff on both sides, but I used a trick, and you've got to pay attention. I used my polyatomic ions to my advantage. I made this easier by keeping them together. All right? And that's what we did here. Type of reaction, of course, it's a double replacement. How do I know? Because I've got what? Positive and negatives on both sides that can double replace. Is 8 a double replacement? And the answer to that is, of course it is. Positive and positives. Is 9 a double replacement? Well, this one is a positive and negative. What about, there's only 1 of them. So only 1 can replace. And you can guess what that is. So what I would like you guys to do is to stop this video. Actually, I'm going to be done, okay? And I would like you to continue on trying to balance the rest of these, all right? And there is a key that goes with the back side to see how you're done. I do expect you to get some of these wrong and have a little bit of trouble, and that's why we have some teachers to help you with this. But hope you understand the basics, okay? All right, take care.